Okay, this is sample CRS.C20, and I'll actually be doing this problem twice, once today and again tomorrow, because we're going to look at column space and row space. So I'm just going to do the column space today, because today's homework is just going to focus on the column space parts of this section CRS, okay? Okay, what we want to do is find a set of vectors x such that the span of x gives me the column space of vector A. That's what this symbol is. So this is the column space. And the column space is a span itself. So we want a set of vectors x such that its span is equal to the column space, which is itself a span. Well, this is super easy because it's real brute force. And that is, if I just wrote the four column vectors, that could be our set x. So I can say x is equal to the set of vectors 1, 0, 1, 1, followed by 2, 1, negative 1, 1, oops, negative 1, 1, 3, 1, 2, 2, and finally, the last column vectors 1, 2, 3, negative 1. So that does the trick. That could be our answer. Of course, this particular set is not linearly independent, so it fails for that reason. The second reason is these are just the column vectors that make matrix A. So the column vectors themselves will always comprise a complete span. The problem is, just like we found out in the last chapter on vectors, this is overkill. We don't need all four of these vectors to span the same set that the span of x actually contains. Some of these are unnecessary, and they're not linearly independent. I'm not going to check that right now, but I'll show you if we do the test for linear independence while we're forming this column space, we'll see that this full vector set is not linearly independent. So what do we do? Well, our old friend, the reduced row echelon form, is going to tell us an awful lot. So if we RF A, this is what we get. So you get 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and then the final column is negative 7, negative 2, 4, and 0. So this is what the reduced row echelon form of matrix A looks like. And you can see we've got pivots in rows 1, 2, and 3. So if I were going to write out the set of D, the dependent variables are 1, 2, and 3. Well, that also tells us that these three columns will form a linearly independent set. Column 4 won't, only because row 4 produced all zeros. It provided us with no information. So I can see that I get a single solution for the first three vectors, or for the first three variables, and of course I get a variable solution for the last one. So that means that the columns that were represented by these are the minimum columns necessary to not only give the whole spanning set, but that they're also linearly independent. So that's what I do, is I go back to the original matrix and I take column 1. So that's 1, 0, 1, 1. I take column 2. So that's 2, 1, negative 1, 1. I take column 3, and that's 3, 1, 2, 2. And that's it. I don't need to add on the fourth column because it was superfluous. That is, this will give me the same spanning set as this first choice of x. Not only that, this has the advantage of being linearly independent. How do I know? Well, because if I were to put this through the RF process, I would get the identity matrix, which is the definition of a linearly independent vector set. So there we go. That's all that's needed in order for x to span the column space of A. I don't need to brute force it. I can actually get away with a smaller vector set, and the RF was the key.